Today we will discuss about semi-empirical mass formula. Actually, this is a continuation of a liquid drop model. Okay, Bohr and Wheeler, they have explained the liquid drop model. Whittaker obtained the expression for the binding energy by using so many facts and figures. He has explained how we are going to determine the binding energy here. Binding energy of a nucleus. Binding energy of a nucleus. Okay, the binding energy of a nucleus, Whittaker, he has explained and he took that as a challenge and he got the expression for the binding energy of a nucleus. What is that? We are not going to derive everything here now. Only the basic ideas we are going to understand about the concepts. So first idea, binding energy. Point number one. Binding energy of a nucleus, it is directly proportional to the mass number. Binding energy, A is said to be the mass number, don't forget. A is mass number of a nucleus. Z is atomic number of a nucleus. Already we know all these concepts. Capital A representing the mass number, Z representing the atomic number of a nucleus. So binding energy of a nucleus is directly proportional to mass number. As the mass number more and more, number of nucleons are also more, protons number and neutrons numbers, it's go on increasing. As the proton number and neutron number is go on increasing, binding energy is also go on increasing. Okay. Therefore, binding energy is equal to a constant of proportionality. I will going to put it here. That proportionality is A, small a into capital A. Okay, first point. Second point, number two. The binding energy depending upon even the surface nucleons. Surface nucleons numbers is more and more. If I am considering on the surface, the number of nucleons are more and more here now. Then the binding energy is go on decreasing. If the nucleons are well present inside the nucleus, instead of surface, if they are present well inside the nucleus, binding energy is going to get increased. But binding energy is go on decreases as it is present on the surface of a nucleus. And the surface is go on increasing as the radius is go on increasing. Therefore, I can say the radius, already we know about this, the radius of a nucleus is directly proportional to mass number raised to the power 1 by 3. Radius of a nucleus. And the radius of a nucleus is equal to R0 into A to the power 1 by 3. We know all these things. Using these two ideas, I can write surface energy. That is ES. The surface energy is equal to here, or it is directly proportional to, I can write A to the power 2 by 3. Capital A to the power 2 by 3. Using this one, this is having a positive effect, don't forget. Binding energy is go on increasing. As mass number increases, binding energy is go on increasing. But here is not like that. As a surface, a number of nucleons are more and more here. Now, this is go on reducing here. Binding energy is go on reducing here. This is said to be negative, therefore. So, therefore, I can write here ES is equal to surface energy or surface area. I can consider here. It is equal to minus B is a constant. Negative sign indicating as it is go on increases, binding energy instead of increasing, it is go on decreasing here, negative effect, minus B into A to the power 2 by 3. Okay, this is negative. This is this second concept, that is second concept. The third concept, what is that third concept here now? Number 3. Okay, binding energy is proportional to here Z into Z minus 1 divided by A to the power 1 by 3. Okay, yes. It is an electrostatic force. Actually, Z means atomic number. Atomic number representing the number of protons. Z representing the number of protons. As the proton number is go on increases here, binding energy is go on decreasing, because we know that between one proton to another proton there is a electrostatic repulsive force is also existing here. Between the protons and protons, electrostatic repulsive force is existing. Using this one, I can say binding energy is said to be negative value. Okay, as number of protons are more and more here, binding energy instead of increasing, it is go on decreasing, because of the electrostatic force of repulsion is existing between the proton numbers. Okay, therefore I can write binding energy, or I can say this is taken as, or maybe E suffix C or something, we can write that concept. Okay, that is a Coulombian force, that is equal to minus C, constant of proportionality, Z into Z minus 1 divided by A to the power 1 by 3. Don't forget, due to that one, binding energy is go on decreasing. Fourth point, number 4. What is the fourth point here? The fourth point indicating that depending upon the number of neutrons, depending upon the number of protons, the number of protons or number of neutrons, is it even number or it is odd number, depending upon that. Okay, if number of protons is equal to the number of neutrons, that particular nucleus is said to be more stable. The maximum stability, you can see that whenever the number of neutrons is equal to the number of protons inside a nucleus. Okay, if there is a lack of symmetry, if it is present between the number of protons and the number of neutrons inside the nucleus, which decreases its stability. Once the stability decreases here, binding energy is go on decreasing. Binding energy means stability, nothing else. So in this case here now, E alpha is equal to D into N minus Z, that square divided by A, where D is a constant and this is also negative. Of course, this produces binding energy as negative. Okay, D is a constant, N is the number of neutrons, Z is the number of protons. If number of neutrons and protons, if they are equal to each other, this value is equal to 0. N is equal to Z means this is equal to 0. 0 means E alpha is equal to 0. So binding energy is negative here. Depending upon even nuclei, or maybe it is odd and odd even nuclei, depending upon that. I mean to say that number of neutrons and number of protons. Number of neutrons and number of protons. Okay. The fifth point is said to be regarding the delta here. Delta here. For example, if it is calcium 40 and 20, if I'm considering here as an example. Okay, this is a nucleus. This nucleus, if I'm considering, this is containing 20 protons and this is containing 40 minus 20 is equal to 20 neutrons. 20 is an even number. 20 is an even number. And even nuclei, if it is said to be existing, it is having more stability. This is an odd and this is also an odd number here, then it is said to be lesser stability. Even one is even, the other one is odd, there is a lesser stability is present. Therefore, whenever if you are calculating the binding energy for a calcium 40-20 for this particular nucleus, binding energy we are supposed to take with a positive sign only. If it is an odd number, we are supposed to take binding energy as a negative sign. So you should not forget about this. Now combine all these things together. Let us combine all these concepts together. Together I will going to write all the 5 components. Binding energy is equal to all the 5 components together. We can write binding energy is equal to first component small a into capital A with a positive quantity. Second one minus B capital A to the power 2 by 3. Third component with a negative sign again, C into Z minus 1 divided by A to the power 1 by 3. Fourth component minus D into N minus Z square divided by capital A. Fifth component, either it is plus or it is minus. I said already, some occasions maybe it is positive, some occasions it may be negative. For calcium 40-20, I can write it is said to be positive. Okay, so positive or negative, delta is a constant divided by a to the power 3 by 4. This can also be written, don't forget, this can also be written. Either we can write it like this. We can write it like this, binding energy, or we can write the binding energy as like this. E binding energy can be written as AV, volume constant, into capital A, minus AS, surface constant, A to the power 2 by 3, minus Coulombian force, AC, Z into Z minus 1 divided by A to the power 1 by 3, minus A suffix D here, A minus 2Z. We can write, instead of N minus Z, we can write A minus 2Z. A minus 2Z, that's square, divided by capital A, where A is mass number, 2Z, Z is the atomic number here, that square divided by A, that is equal to this. This and this, they are one and the same. N minus Z square divided by A or A minus 2Z whole square divided by A, they are one and the same. Last part, okay, fifth part, plus or minus, don't forget. Okay, depending upon it is an even or it is odd number, odd and odd. Plus or minus here, AP parity, A to the power minus 3 divided by 4. So using this empirical mass formula, semi-empirical mass formula, we are solving the problem. Problems that is also important, equally important. Problems are also having equal importance here. Okay, not only this theory, problems are also important. Okay.